Okay. Well, good day, everybody. I'm Amy Lambert, EA's Director of Communications, and welcome to this webinar focused on the tangible benefits of thermally treating PFAS-impacted solid materials. Next slide, Frank. Before we begin, I'd just like to go through a few housekeeping items. Your microphones have been muted and video disabled. To ask questions, please use the chat feature. We'll be holding all questions until the end of the webinar and answer as many as we can, but you can feel free to add them into chat as we're going. This presentation is being recorded, and we do plan to post this video to our YouTube channel as well as our website within the next week. Now, I'd like to introduce today's speaker. Dr. Branco is a Senior Vice President and Director of Quality Control at EA. He has a BS in Geology from Duke University, an MS in Geology from the University of Texas, Arlington, and a PhD in Environmental Science and Engineering from the Colorado School of Mines. Dr. Branco is a licensed professional engineer in Maryland and a professional geologist in New York and Tennessee. His professional focus relates to contaminant fate, transport, and cleanup of environmental contaminant source areas, and groundwater cleanup of organic and inorganic contaminants. He specializes in innovative in situ and ex situ cleanup of contaminants of emerging concern and serves as principal investigator on EA's PFAS research related to thermal treatment. Frank, I'll hand it over to you.
Thank you, Amy. I'm pleased to be here. Thank you for listening in today and hearing what we can offer on our experience on thermal treatment and some of the work we've done on a research angle with both the CERTIP and the ESD programs, ESTCP programs with the Department of Defense. So just going back to the title slide, I wanted to mention what's shown on this slide. Some of you might be familiar with seeing aqueous film forming foam distribution systems inside of buildings. We've all seen pictures of buildings almost completely full of AFFF. The release of AFFF often leads to site conditions where soils are impacted with PFAS, and large-scale systems like what's shown in the center figure here. This is a big thermal desorption, thermal oxidation facility that operated not on PFAS, but on petroleum organics and chlorinated volatile organics at George Base Cape Cod by one of our team members, TDX, and also Clean Earth operating the system. This is very similar to what I'll be discussing later on in the presentation on full-scale thermal desorption, thermal oxidation. And I've titled this talk, "The Tangible Benefits of Thermally Treating PFAS-Impacted Solid Materials." One, because the thermal treatment in general for PFAS is the most common remediation technique and the most logical remediation technique that might be available, because thermal technologies will destroy PFAS, as you'll see in this presentation and maybe as you recognize with other work. The benefits of treating both impacted soil and spent granular activated carbon, and also potentially wastewater treatment biosolids. It's tangible because if we're destroying PFAS, then it's possible that soils and other solids could be reused at sites, granular activated carbon and soils. The reuse potential is a big aspect of what we consider a tangible benefit of thermal treatment technologies. Now, although that many of these thermal technologies might be mature, they haven't really been evaluated for the use with PFAS-impacted material, and they're showing great promise and potential for destroying PFAS, but the removal efficiency, the transformation mechanisms, the formation of incomplete combustion products, and the potential emissions are still really in their infancy with regard to full-scale work or even pilot-scale work to some degree. So we'll talk a little bit about that. I've already talked really about the tangible benefits. So let me move on here. For the agenda for this talk, I'd like to introduce PFAS and define it for those that really aren't familiar with this topic. I think we're very much familiar with PFAS today, so we won't spend much time on that. We're going to talk about stability and bond strength of carbon-fluorine bonds and why thermal is an appropriate set of technologies for addressing that stability and bond strength of these compounds. We're going to talk about thermal transformation mechanisms to some degree. This is not a talk about the research related to transformation of PFAS or the initiation of transformation, but I'd like to introduce the topic. I'd like to also introduce some thermal treatment technologies and what we're aware of today that's being researched or piloted or initiation of full scale. And then we're going to talk a little bit about lab scale results and the scale up of that to the intermediate scale experimentation results that EA has been involved in with the CERTIP and the ESTCP programs. We're going to talk about those results and finish that off with a summary and a look ahead for really what we're planning on next, at least with thermal disruption, thermal oxidation. So again, most of you are familiar with this, but it's almost laughable how many synthetic fluorinated compounds we're up to with PFAS. The number that I've seen recently is as much as 15,000 different PFAS compounds. The ubiquity of these products is truly amazing. They were incredible at water and oil repellency and chemical repellency, temperature resistance, and reduce friction, and basically in most household goods as well as food packaging, and then their use in aqueous film forming foams is notable. So the most studied PFAS compounds include the perfluorocarboxylic acids and the perfluorooctane sulfonic acids, or PFCAs and PFSAs. And then you could see I have some ITRC information here about the definition of short and long change on the PFCAs and the PFSAs. Two of the most heavily studied compounds from a fate and transport perspective and also from the toxicity and treatability is PFAS and PFOA that are shown on this slide, on the right side of the slide. A little bit about the stability and the bond dissociation strength of the carbon-fluorine bond. As you may or may not know, the carbon-fluorine bond is one of the strongest and stable organic chemistry bonds that's in existence with these synthetic organic molecules. We're talking about bond strengths and bond dissociation strengths of about 130 kilocalories per mole. You could see in this table some other bonds and what their bond dissociation energies are. Part of the reason why the carbon-fluorine bond is so strong is because of the electronegativity of the fluorine atom. Increasing the number of fluorines in a PFAS molecule the number of fluorines attached to the same carbon requires, in general, more temperature to destroy that carbon-fluorine bond. So the bond dissociation energy probably goes up when you're talking about more fluorines associated with a single carbon. It's also of note that the shielding of carbon by fluorine also contributes to that thermal stability, increasing the bond dissociation energy. A useful table and some of the references on the bond dissociation energies, you'll probably find that these vary quite a bit, not significantly, but they do vary with regard to the standard operating conditions and the conditions of the experimentation in which the bond energies were understood, or the computational aspects of how the bond associations were identified. Just to put this in perspective on kilocalories per mole, or 130 kilocalories per mole, an equivalent for a human calorie burn, unrelated to PFAS impacts, but just putting it in perspective, we're talking about a human calorie burn when we're talking about 130 kilocalories per mole, of about half of running a marathon for 1 mole, or basically 500 grams of a typical PFAS molecule like PFAS. So hoping that just puts it a little bit in perspective how much energy we might be talking about, and why thermal energy is required to break these bonds. I want to talk a little bit about the thermal transformation mechanisms. Again, this isn't a talk about the research work related to transformation, but I wanted to discuss a little bit about the initiation of transformation mechanisms as it relates to thermal technologies. And first, I wanted to point out that temperatures at which PFAS molecules typically volatilize may be higher than at which they start to decompose. So some of the technologies that rely on volatilization or desorption, like thermal desorption, you actually may get some decomposition occurring before the desorption of the volatilization occurs. That's an important point. The transformation and decomposition aspect has been largely overlooked until about, something about like 7 years ago, where a number of researchers, including Khan et al., Wu et al., and Xiao et al., which are shown on this slide on the sources of some of these transformation products, have started to do some research. This is all research on this particular slide that's from 2020 on. Before I talk about the slide, let me just mention that some other general points. PFAS transformation with incomplete combustion likely occurs at lower temperatures and residence times, while some but little is known about the transformation products and mechanisms. So when we're talking about lower temperatures and lower residence times, we have a greater likelihood of some of these potential for incomplete combustion products occurring, and less information about what mechanisms led to their creation. Fourthly, the temperature required to initiate decomposition largely decreases with increasing chain length. So the shorter the chain length, for instance, molecules like tetrafluoromethane require a higher temperature to decompose those shorter chain products. So the last point here is that the temperatures and reaction times can contribute to incomplete thermal destruction, resulting in these short chains. So sometimes, as tracers, we look at these short chain compounds in air pollution control systems like thermal oxidation to see if breakdown occurs with these shorter chain molecules. Thereby, we know that we're getting destruction of longer chain molecules. The figure that's shown on the right is, again, just a couple of examples of some transformation products, transformation mechanisms that were shown by a couple different researchers. Again, this is not a total treatise of these transformation products, more just shown for example. But Wu et al. On the top has shown that PFAS transformation pathways under thermal input in an alkaline environment. So this is the pathway that you would get under that alkaline condition for PFAS, with an initial step where you lose that sulfonate head group and form an alcohol, and then the alcohol then produces a ketone as more hydrogen fluoride is cleaved off, and then finally you get to these perfluorocarboxylate shorter chain molecules. And then Khan has also shown that under computational scenarios, that PFAS pathway, not under alkaline conditions, under normal pH conditions, actually just leads to the defluorination, and then the breakdown of the molecule by a defluorination step. And then with PFOA, this was shown by Xiao et al. In 2020, that basically the loss of a fluorine occurs under a step where a carbon-carbon bond is actually broken as a later step, and then you get these shorter chain molecules after breaking the carbon-carbon bond, and as you reduce the size of the molecule. So again, let me move on. I want to talk a little bit about treatment techniques in general, and then we'll dive into more specific work that I conducted as a principal investigator for SERP. Some of the treatment techniques. This is again just a summary. I think that it's fair to say that in most review papers that I've really poured through, there are four major categories of technologies that we would consider with thermal treatment of PFAS-impacted material and PFAS-impacted solids. They would include a combustion, which is thermal in the presence of oxygen, pyrolysis, which is thermal in the absence of oxygen, gasification, which is thermal, where you starve the oxygen, you use air, but you have low oxygen content, and then hydrothermal, which is a technique where you use low temperature and high pressure and heat, and basically you go through an acid or a base catalyzed reaction. So what we're showing on this slide is some specific technologies that rely on one of those four techniques. I want to talk about some of the individuals with regard to treatment temperature and treatment retention time, because those are important parameters for defining the breakdown and whether you get complete mineralization of PFAS or not. Thermal desorption has been used at least in pilot testing for in situ, and it also could be used for ex situ soil treatment. We're looking at treatment temperatures by some of the folks, including Crownover et al. 2019 and Lind et al. 2018, temperatures between 150 and 550 Celsius. The residence times can be as short as 15 minutes, but we're generally looking at lower temperatures of very long residence times of 10 to 14 days in order to achieve some degree of transformation, or I should say removal of the PFAS compounds from the soil. And then thermal desorption can be coupled with thermal oxidation, which we'll talk about in a few slides. And largely that would apply to ex situ soils, spent granular activated carbon, or sewage sludge or wastewater treatment biosludge. And these are the specific parameters that were identified by some of the pilot studying that we performed, EA's performed. We're looking at desorption temperatures of 500 to 650 Celsius, thermal oxidation temperatures in the secondary treatment of 900 to 1,000 degrees Celsius. The desorption residence times of the soil are on the order of 60 minutes to as much as 95 minutes. The thermal oxidation residence time of the exhaust phase is about 2 seconds, and I've listed the reference for my SERTA project. Incineration. Here we're talking about a broader list of solids, including some that are true waste, spent textiles, carpets, municipal waste, some liquids as well can be treated in incineration. We're talking about incineration temperatures of 900 to 1,100 degrees Celsius with roughly 30 minutes to an hour of residence time. Fair amount of work that's really qualified the incineration of PFAS compounds. I want to also mention that besides the Chawa and Watanabe reference, Mike Christenberry et al. Has submitted an article for the ANWMA magazine that'll be in the May 2024 issue of the EM magazine for testing at a hazardous waste incinerator for PFAS destruction. Smoldering combustion, soil, GAC, and sewage sludge a broad range of temperatures from 260 to 900 degrees, a broad range of residence times, the pyrolysis and the gasification, again, broad range of temperatures, fairly broad range of residence times, although shorter residence times than thermal desorption. And then this hydrothermal liquefaction technique with sewage sludge, plant biomass, relatively broad range of temperatures tested, and a narrow window of residence times that probably can be scaled up to a larger scale. Talking a little bit about the lab scale studies. Again, this is not work that I performed, but one of my co-PIs, Pavan Chawla, was involved in this work with Feng Chao, published in 2020 on the thermal stability and decomposition of PFAS from spent granular activated carbon. A number of different classes of compounds were evaluated or analyzed, all from sorb to Calgon F200 carbon, spent carbon. The work was conducted in part by looking at thermogravimetric analysis, and in particular looking at the stability of different compounds or classes of compounds. You can see, very interestingly, there is a large breakout based on the type of compound, whether it's the carboxylic acids or the sulfonates. The carboxylic acids seem to break down instability at a much lower temperature than the sulfonic acids. PFCAs as low as the initiation of thermal breakdown at 100 degrees Celsius, where the sulfonic acids don't start till well above 400 degrees. This is a significant finding. You can also see that result when you're looking at not just the decomposition, which is shown in the right graphs of PFOA and PFAS in the black line, where you're looking at the decline of PFOA and PFAS. These studies by Feng and Chawla also showed the production of organofluorine products or transformation products that are shown in the maroon line as the decline in PFOA and PFAS occurred, as well as the yield of total fluorine or inorganic fluorine rose dramatically at a later stage when you get breakdown of some of these organofluorine byproducts. So this was an interesting body of work, but it clearly showed that there's a difference in the temperature, at least of the initiation of the decomposition, when you're talking about the desorption off of granular activated carbon. Okay, I wanted to spend most of the time on this talk really going through some of the intermediate scale experimentation that EA's performed with the SERTIP program with DoD. For those of you who haven't seen this work yet, you can go to the SERTIP webpage and pull up the final report that we have on the work that was conducted between 2018 and 2020 on thermal desorption, thermal oxidation. So the notion of this work that was initiated in 2018, when there really wasn't many pilot scale studies on thermal treatment, there were 5, I think, awarded under this SERTIP program in 2018 to study different thermal mechanisms, thermal desorption, thermal oxidation being one of them. But basically take soil containing a typical suite of PFAS as well as a typical aqueous film forming foam or AFFF formulation, and under very controlled conditions produce a proof of concept design for a pilot scale study to look at the following objectives. Can we take soil that had relatively high concentrations of tens of parts per million of individual PFAS compounds and treat it to low parts per billion levels based on thermal desorption, thermal oxidation? So that was step number one, is can we treat those soils, and can we treat them to low enough values where the soils could be reused on site? Again, sort of the tangible benefit angle. Can we effectively destroy PFAS precursors from AFFF within the soil? Can we achieve a destruction removal efficiency of 4 nines or 99.99% for the selected suite of PFAS studied? For those of you not familiar with DRE, I have a slide on that a little bit later on in defining it. And then lastly, as we've been working on for several years, can we design sort of a scalable cost mechanism for determining how much thermal desorption, thermal oxidation will cost for on-site treatment of soils based on treating large volumes of soils at a site? A little bit about the technology description for thermal desorption, thermal oxidation. This is a relatively mature technology that is just now in the last 5 years being applied in a novel capacity to PFAS-impacted material and whether it can treat those materials. The treatment system is partly a primary treatment unit, which is a big thermal dryer to desorb and partly transform the PFAS compounds in soil and remove those PFAS constituents to an air phase. And then the air phase is then going on to an air pollution control system where you remove particulate through cyclones as well as a baghouse. And then there's also a thermal oxidation process where the PFAS compounds are heated to a higher extent and then broken down within the thermal oxidizer. And then you have stack emissions. So there is air permitting to address, and we'll come back to that. We'll talk a little bit about that. The soil itself is just cooled with water prior to stockpiling and then reuse of the soil after meeting cleanup criteria. Interestingly enough, this system that we designed on full-scale applications is a zero emitter as far as water is concerned. All the water is reused in the system that is input into the system. There is a water requirement of roughly 10 gallons per minute input into the system, but there is no water effluent that is emitted from the system. A little bit about the technical approach of the pilot scale study. I know there's sort of a lot within this slide. Let me break it down for you. I had mentioned that we were addressing individual PFAS constituents in the study. These were reagent grade PFAS compounds that were actually spiked into clean soil. And then also we received some AFFF from I show you on the next slide a particular academic institution that's studied it heavily. The soil was treated with these two different spiked solutions to two different temperatures based on our research work that defined that we need to achieve roughly 500 to 650 degrees Celsius to desorb or volatilize the PFAS from the soil. And then within one subset of the experimentation, the subset in which we treated at 650 degrees, we performed a variety of exhaust source testing, in which we were using the most advanced technologies for source testing at the time of emissions testing. Those were modified method 537 for the PFAS compounds in the exhaust, and method 26A, which is for hydrogen fluoride analysis. We expected that based on these temperatures of the thermal oxidation at 1,000 degrees Celsius, that we would be converting all of the PFAS eventually not knowing all of the transformational steps, but eventually converting it to hydrogen fluoride. So the notion was to analyze hydrogen fluoride to understand the fluorine balance. All soils, both feed soils were analyzed, feed and treated soils were analyzed, even though we knew what the concentration of the PFAS compounds were in the spiked solution going into this. So that was one of the real conveniences of this study, is the known amount of PFAS and fluorine that we're adding into the system, as opposed to using impacted soil from the site, where you're quantifying targeted and maybe non-targeted compounds and identifying the hidden precursors through total oxidizable precursor assay, but not necessarily identifying all of the fluorine input into the system. And that helped us with this mass balance. Just the study materials, I mentioned that we used AFFF that was well quantified. Big shout out to Matt Simsick at the University of Minnesota, who provided a 1997 3M variety of dilute AFFF. You can see over here, based on the concentrations, that the AFFF was PFAS based. It was an older form of the AFFF. And almost all of the mass within this concentration within this AFFF was PFAS. But there also were a range of fluorotelomers, PFCAs, and PFSAs, both short and long chain on the PFCAs and PFSAs. So we're trying to look at a range of different compounds from chemistry constituent perspective, as well as their chain lengths. As far as the individual PFAS compounds bought from reagent grade materials, again, PFCAs and PFSAs, range of different long and short chains that were identified here. You can see what the concentrations were in the aqueous solution that we spiked into the soils. A little bit of information down here in the footnotes on dissolution if you're attempting in a controlled way to dissolve some of these compounds. PFAS dissolves very slowly, even if you're well below saturation conditions of PFAS. And then on the basically the sampling, the testing approach here, we tested 10 different experiments that ranged with soil concentrations from starting in feeds from 10 milligrams per kilogram of individual PFAS constituents up to about 20 milligrams per kilogram in the soil phase. These are the targeted, this is the actual, after actually mixing up the PFAS in an aqueous solution and then delivering it to water, to the soil. So the range of concentrations are close, but not exactly like the targets that we planned on. And then here are the two different temperatures that we tested, 500 and 650 degrees, which are in the range of the optimal temperatures. One more slide on the approach. I mentioned this was intermediate scale. So basically we took about 5 gallons of soil, of sand, of clean store-bought sand that did not contain any organics. It also does not contain significant inorganics beyond silicon dioxide, and put that in an electric mixer. We mixed up about 10 gallons at a time, but that was for 2 different batches until it was thoroughly mixed. We manually loaded 5 gallons of the PFAS impacted soil into a batch reactor here, which is a dryer with a rotating paddle inside of it. The system basically was run, this is what akin to an indirect fired system. So it was in an anaerobic environment. We purged this with nitrogen that's ongoing while we're heating this dryer, and the nitrogen purge would then remove the volatilized compounds put them through piping, and send them off to a thermal oxidizer that's sitting on the back side of the primary treatment unit here. So here's sort of the conceptual figure of the entire system. You have the sealed desorber drum that's anaerobically purged with nitrogen, and then the volatilized gas is vented only over several feet to a thermal oxidizer that's sitting basically on its side here. And this is about 20 feet long. Again, has about a 2-second residence time. The dryer temperature, again, was 500 and 650 degrees Celsius with a residence time of 95 minutes. The thermal oxidizer had a residence time of 2 seconds and 1,000 degrees Celsius. On this slide, you're looking at the temperature ramp up of the soil. The red line is for the soil. Thermocouples existed also within the outside of the dryer cylinder. And also, this is the thermal oxidizer in the blue line. But pay attention here to the red line, which is the temperature of the soil. We started with ambient temperatures of the soil. Since this was batch loaded, you get an initial increase in temperature, and then plateaus during the basically the evaporation of the water. It holds stable at 100 degrees Celsius during the ramp up, and then when all the water is essentially boiled off, you begin to see ramp up again to this temperature. This curve represents one in which we ramped up to roughly 650 degrees over 95 minutes. So we were measuring the temperature as we go. We made sure we reached the optimal temperature. And I'd like to present the results now. Let's start with the AFFF. The results are shown for both 500 and 650 degrees at the two different temperatures, and you're looking at the results for the AFFF impacted soil here. And what we've done is we've divided the results into total fluorotelomere sulfonates, total perfluorocarboxylic acid compounds, and then total perfluorosulfonic acid compounds. And the blue bars represent the untreated concentration. The brown bars represent the treated concentration. You could see this is in log scale. So even though this difference doesn't look significant, recognize that it is roughly 2 orders of magnitude different for most of these changes from untreated to treated soil. Some generalizations. The AFFF was composed in targeted analysis. We did not perform non-targeted analysis on the AFFF of 24 quantifiable compounds. All were included in the analysis of the spiked versus the treated soils. We're only showing soil data here. This is not exhaust data yet. And the percent reductions were relatively high for both temperatures. You could see that even when considering 500 degrees, we were somewhere between about 97.2 and 99.9% reduction of either FTS, PFCA, or PFSA. But some interesting trends kind of break out here. The higher reductions were observed for the fluorotelomere sulfonates and the PFCAs at 650 degrees relative to 500 degrees. So you can see that the percent reduction for 650 is 99.9% versus 97%. That's what I mean by that bullet. And that this is an important point. The relative reductions that you see at a given temperature between the PFCAs and the PFSAs, although it seems measurable, error bars are not shown here, it's probably not significant between the PFCA reduction and the PFSA reduction, because this is a bit inverse of what we expect to see, where PFSAs generally show a little less reduction in soils at a given temperature. And I'll show that on the next slide for the individual PFAS compounds tested. I'm sorry, on the following slide from this one. One more slide that I have on the AFFF results. We performed total oxidizable precursor assay for the feed soils as well as the treated soils. Although this graph is a little complex, let me break it down for you. What you're looking at from sample 1 and 2 represents untreated soil samples. So these are the results of the total PFCAs for the untreated samples. This is pre-TOPA or pre-oxidation. You can see that the concentration pre-TOPA of the feed soil was less than 1,000 micrograms per kilogram. Total PFAS, I'm sorry, total PFCAs for the one AFFF sample. But post-TOPA, when you're looking at post-oxidation, you're seeing a significant rise, as we would expect to see for TOPA results for the untreated sample. You see at least 1 order of magnitude jump in the amount, and this is reflective of the hidden precursors that are showing it with the TOPA analysis. When you're looking at treated samples, this is after thermal desorption. The pre-TOPA result was essentially non-detect on the PFCAs, and the post-TOPA result of importance was also non-detect. So what this is showing is that the precursors that are shown by TOPA or reflected by TOPA are not present any longer in the treated sample, showing that removal of the precursors from AFFF in the soil are occurring based on the thermal desorption technology. Some of the results related to the individual PFAS spike soils. So this is not the AFFF spike soils anymore, but the individual 6 compounds. The results again shown at 500 and 650 degrees Celsius. Again, you're looking at log scales. Blue is the untreated or feed soils. Brown is the treated soils. So what we're talking about, what I mentioned down here in percentages, is removal efficiency from the soils. In general, PFAS removal efficiency at 500 degrees, when you average and take the arithmetic mean, is about 97% for all the compounds and for all the tests conducted under these experimental conditions. Where at 650 degrees, you're looking at about 99.7% removal efficiency. So a higher removal efficiency at 650 degrees. So our optimal temperature of these two appears to be 650 degrees. One other trend that jumps out that's rather interesting is when you look at the sulfonic acids, they're not treated quite as well, or they don't have lower removal efficiencies compared to the carboxylic acids. This is what I was referring to in the earlier slide. The transformation of a sulfonic acid PFAS or PFCAs to other compounds appears to occur with less significance than the PFCAs, although both are showing significant removal at 650 degrees Celsius. But there was a trend here, observable trend on PFCAs showing a lower removal efficiency. When we compared our results, which are shown in this first column, to screening criteria, in this particular case, I wanted to show screening criteria that were reflective of where we performed the work. The pilot testing was performed in Robstown, Texas. So I pulled up the Texas Commission of Environmental Quality, TRP PLCs, or performance cleanup levels. You could see that all of our results for these 6 compounds, and this is average data from the experimental runs in which we received results of that testing that largely represented about 6 different experiments, where our results are below these TCQ values. These numbers have not changed since 2020. The EPA RSLs, on the other hand, have changed significantly since 2020. And you can see that except for PFPEA, which there is no EPA RSL for protection of groundwater SSLs. So these are the most stringent criteria that can be used, the state criteria and the federal criteria. The results of the pilot testing, except for PFAS and PFBS, are below the, PFHXS are below the EPA RSLs. Because these didn't exist at the time, we were not aware of them. They weren't significant at the time. To address them at this point, with there being lower criteria here, we feel that longer residence time or slightly higher temperature will address the treatment of soils to these levels. These are not significantly lower than levels that we achieved with 650 degrees Celsius in 95 minutes. I mentioned about destruction removal efficiency. This is the way to calculate it. It's basically a ratio in percentage of the mass of PFAS in the thermal oxidation exhaust gas divided by the difference between the mass of the PFAS in feed soil and the mass of the PFAS in the treated soil. It is truly a removal of a measure of removal efficiency from the thermal oxidation process. So it's really, DRE evaluates the TO or the thermal oxidation process. We also looked at the organic fluorine DRE, which is sort of a similar measurement when you're looking at just the mass of the organic fluorine versus the entire mass of the PFAS compound. Some DRE results. You could see that what we achieved as far as the two experiments where we did the exhaust analysis was far and away better than the objective of our study. We achieved 5 nines or 99.999% removal based on the DRE measurement from the exhaust. And then for the fluorine balance, we did perform a fluorine balance in the study, and the way that we did it is by knowing the entire mass that we put into the feed soil based on how much we added. And this is only on the reagent grade PFAS, where we had the known amounts of the constituents of each PFAS, 6 PFAS, in the blue bar in a given experiment. And then what you're looking at in the brown bar is basically the mass of fluorine that's accounted for based on the molar ratio from hydrogen fluoride emission from the thermal oxidizer. This is not based on knowing the fluorine mass in all of the processed residuals. The amount of fluorine mass in the soil was insignificant. Remaining mass in the soil, treated soil, was insignificant relative to the mass of the hydrogen fluoride created. And what this basically shows is two things in particular: that when you're dealing with these temperatures of 650 degrees Celsius, the ultimate byproduct or product of conversion is hydrogen fluoride. That's clearly shown here as the mass recovered based on hydrogen fluoride. And it's within the error bars of both the experiments. When you average the two fluorine balances, you get about 99% recovered based on the hydrogen fluoride recovery. The second important point is when you're working at these high temperatures, although research is still uncovering some of those initial transformation products in thermal desorption, when you're looking at thermal desorption coupled with thermal oxidation at 650 degrees or greater and residence times of 95 minutes, one can measure just method 26A, the hydrogen fluoride, to get the complete fluorine balance. There are many studies in which fluorine balances are not quantified as significant as what we have here with our recovery. And I attribute that to several factors. One, we knew exactly how much in the control experiments we were spiking in the feed, which is not particularly true when you're dealing with PFAS impacting material from a site where you have hidden precursors. And then secondly, there are extremely short lengths in this pilot, proof of concept study between the thermal dryer and the thermal oxidizer, and there isn't room for condensation of the byproducts before thermal oxidation. So really, two factors went into this rather significant fluorine balance that really shows this technology to be completely viable here. So in summary, I just want to conclude with a little bit about what I introduced in general in the beginning about thermal technologies. Transformation by defluorination is primarily the mechanism, although and this is a destructive technology, although there is significant research that needs to be done on transformation products. They're not poorly understood anymore, the significant amount of work that's being done on those right now, but it's a difficult field of study to understand thermal breakdown products, considering some of them are not very long-lived. Under the research work performed under CERTA ER 18-1572, or this project that I presented on, the end product is hydrogen fluoride that does need to be addressed from the standpoint of a wet or dry scrubber for full-scale applications. But we've sufficiently defined that hydrogen fluoride represents the fluorine balance, and that as if you address the hydrogen fluoride on emissions, that's the primary PFAS component that needs to be addressed. There are other criteria pollutants that need to be addressed, including NOx or SO2 if there's some other fuel that's being used to fire the thermal desorption, thermal oxidation system. In this thermal desorption, thermal oxidation study, we sufficiently proved, at least in a proof of concept, that we can treat to the part per billion or the sub-part per billion level, that destruction removal efficiencies representing greater than 4 nines can be achieved. And this is allowing what we believe will be site reuse for the soils after treatment. Continuing research is warranted. There is work that's happening currently on another project that we're funded for under the ESTCP program, which is a demonstration project. The field work will be conducted in the summer and the fall of 2024. It's a full scale up to a large scale thermal desorption, thermal oxidation system. Loads of permitting involved. Here we're addressing actual soil from fire training area that contains petroleum and chlorinated co-contaminants, and we're further evaluating exhaust sampling and some of the latest and greatest methods like OTM 45 and OTM 55 eventually for the thermal exhaust, and then using method 1633 for any of the solids that we're evaluating in feed or in process results. So with that, I'll take any questions that anyone has as we conclude here.
Frank, there are already 4 questions in the chat.
Okay.
So
Great.
if you want to open that up, you can read them, or I can read them to you. It's completely up to you.
Why don't you go ahead and read that to me?
Okay. That sounds good. The first question is, GAC is listed as environmental media, but ion exchange resin is not. Are the technologies listed for GAC suitable for IX resin?
So at this point, IX resins have not been tested, and there are other technologies that address IX redevelopment. So I'm not aware currently of any testing for IX resins, but there is no reason why IX resins could not be tested as well for but the parameters of temperature and residence time might significantly vary from what we've observed with granular activated carbon. It's a great question, though, and I'm sure that at some point further research will be done on it, on thermal technology, whether it could be address IX resins in bulk with other media, including GEC.
Thank you. Next question, does the cleaned soil retain physical properties such as plasticity, and are any diagenetic minerals formed?
Okay, so for the first part of that is the how's the soil returned? I mentioned earlier that the concept for thermal dissolved thermal oxidation that EA and TDX are proposing is to remoisturize the soil. So to use that the water that that's left over from the evaporative cooling to actually remoisturize the soil and to cool the soil. And that process of remoisturizing the soil does return some level of moisture content to it. Now, the temperature at which the soil is dried, if we use a temperature of 650 degrees Celsius, we are removing moisture from organic content, but not altering the chemistry of the organic content of the soil. So there is still organic content. There may be some slight transformation of some organic content, but because organics are not particularly volatile and would not desorb at those temperatures, you're not losing organic content from the soil, other than what's just physically introduced into the exhaust based on the rotation or the tumbling of the soil. So not significant. And then as far as mineralization, it largely depends. It's another subject of a great research project or projects that could occur here. It largely depends on what the original mineralogy of the soil is present, what inorganics are present in the soil. I did not mention in the study that calcium has been heavily studied as far as its use for actually lowering the temperatures in thermal decomposition. So calcium in particular is being looked at with these types of research studies, but could it alter diagenetically alter the soil? I guess that's entirely possible, but not the part of this pilot study at this point in time, and probably study further research on this.
Okay, thank you. Next question is, given the high temperature needed to completely destroy PFAS, did you look at sustainability and energy sources and how to account for these in projects requiring green practices?
Yeah, another great question. There is an ongoing effort by EA to actually compare soil treatment by thermal desorption, thermal oxidation, which is energy intensive capital investment, but short-term effort as far as remediation to some other technologies that rely on long-term treatment in situ, like much longer time frames. The preliminary analysis is showing that it's essentially a break-even effort. It's a net sum game on capital investment and energy intensive use on thermal oxidation versus long-term in situ treatment. So there are benefits here, even though it seems to be energy intensive in the time frame of cleanup. I recognize that it may not be viable for every project, but a site that's going to be, say, redeveloped, in which there's human exposure, this may be worth the capital investment and the if the drawback, if you will, on the sustainability side. We're continuing to look at how to make this less energy intensive and to preserve energy in the system. So, and there are ways to do that. I just think we're too early on here to recognize that.
Okay. And last question that's in the chat. Have you found this to be a preferred option in treating carbon activated filters, parentheses temperature range, and utilizing treated soil for topsoil applications, parentheses sterilization?
Yeah, great. I think I understand the question. If I could, I'll try to repeat what I believe the question is. For soil treatment, a technology like this, in which these systems that I've shown pictures of earlier on here, going back to our title slide, these are relatively large systems. This is about a 2 acres in size area of limit of disturbance with direct fired thermal desorption coupled with thermal oxidation. You're talking about a throughput of about 30 tons per hour. This is the type of system that could treat large volumes of soil, like an entire fire training area, or soil that's impacted by a fire training area, and thereby eliminate the source of the PFAS plume in groundwater. Recognizable, this is not necessarily the right size of a piece of equipment for treating a couple drums of granular activated carbon, which could be treated by a smaller scale thermal desorption, thermal oxidation system, or a thermal desorption system with some kind of treatment on the exhaust phase. We're currently trying to couple the thermal desorption with a smaller scale system to actually treat batch scale volumes, much like our pilot scale, that are only a couple hundred gallons at a time, more of like a milk run approach, that you could treat soil IDW, that's just a couple of drums, or granular activated carbon, which is significantly smaller in volume than these large scale systems. So thank you for asking that question, because I did not put this system in the scale of what we would attempt to use for. This could treat hundreds of thousands of cubic yards of soil at a time, for depending on the length of the project.
Okay. One more question that came in. Nitrogen gas preferred over natural gas in the process due to getting higher temperature?
Well, the nitrogen gas is a purge, so it creates the conditions of pyrolysis. So it's a purge for the exhaust to push through in the dryer, where natural gas or propane is the fuel that fires that dryer, creates the thermal energy. So there is a big distinction between the two.